Hello, Professor Pelkey. Because of the size of this board and the lighting in here, it's almost impossible for me to set my phone up so that you can view this presentation properly from one position. Because of this, I'm going to go from step to step carrying the phone with me and describe the mechanisms as I go through it. Firstly, we're talking about the Hofmann rearrangement and the Curtius rearrangement. These reactions both share a common product in an amine. The Hofmann starts with an amide, and the Curtius starts with an acid chloride. So firstly, if we look at the Hofmann, it's conducted in basic conditions and it loses a carbon. Dissimilarly, the Curtius is conducted in neutral conditions, but it also loses a carbon. Alrighty, so getting to the mechanisms. If we start, we're just going to do a generic mechanism here. If we start with our amide and we deprotonate it with the OH, we then have a negative charge on our nitrogen. It forms a double bond with the carbon, breaking the pi bond with the oxygen. Our oxygen then has a negative charge. It forms a pi bond again with the carbon, breaking that double bond with the nitrogen. The nitrogen then forms a bond with one of the bromines from the dibromo, resulting in this structure. Then the OH deprotonates the nitrogen, primarily because the bromine is an electron withdrawing group, resulting in this structure with a negatively charged nitrogen that forms another pi bond to the carbon, breaking the pi bond with the oxygen again, leading to this structure, which is the one that rearranges. This is the complicated step. And in this step, we see our R group form a bond with our nitrogen because it's kicked off of the carbon when this oxygen forms a pi bond with it. So then the R group migrates to the nitrogen, and the nitrogen breaks its bond with the bromine because it's an excellent leaving group. We then go on to this structure, which is called isocyanate, and this is a structure that's shared between both reactions, and I'll talk about that in a second. But in this structure, we see the OH attacking the carbon with 2 pi bonds on either side, and it's got a partial positive charge, and that's why the OH attacks it. So that results in this structure, and because it breaks a pi bond with this oxygen here, leaving that negatively charged. This structure forms resonance with this structure, and then from this structure, we see that nitrogen is negatively charged, and it gets protonated from the water in solution, resulting in this structure. And now we have OH in solution because one of the hydrogens has been taken from the water by the nitrogen. That OH deprotonates the alcohol down here, resulting in the oxygen there being negatively charged, causing this group to leave, causing the oxygen to form a double bond with this carbon, causing it to break its group bond with nitrogen, resulting in the group to leave, leaving our R group bonded to a nitrogen and a single hydrogen with a negative charge. This nitrogen then takes a hydrogen from the water, resulting in our amine product. Alrighty, moving on to the Curtius reaction. The Curtius rearrangement, my bad. So here we start with an acid chloride. It's a neutral solution, and it forms essentially the same product if we were to start with the same R group in amine. Alrighty, so starting from this group here with our acid chloride, we say our sodium anazyne, I forget how to pronounce it, with 3 nitrogens double bonded to each other, leaving the 2 on the end negatively charged. One of those negatively charged nitrogens is going to bond to this hydrogen, break the pi bond with the oxygen. That results in this structure, and that oxygen double bond forms another pi bond with the carbon, kicking off the chlorine, resulting in this structure here. And we see that these 2 nitrogens, one is positive, one is negative. To resolve this, the negatively charged nitrogen forms a triple bond with the positively charged nitrogen, breaking that nitrogen's bond with the neutral nitrogen bonded to our carbon over here. This is a resonance, resulting in this structure here with the negatively charged nitrogen forms another bond with the carbon, breaking the pi bond with the oxygen, resulting in this structure. And this is similarly the structure that we're going to see rearrangement from. And in this, we're going to see The oxygen, once again, similarly to the Hofmann reaction, form a pi bond with the carbon, removing the R group, causing it to migrate to the nitrogen here, additionally breaking the single bond with that nitrogen and the N2, soon to be N2 gas, which is an excellent leaving group. I should mention that. And then we see our R group bonded to our nitrogen, pi bonded to a carbon that is then pi bonded to an oxygen. From here, we see H2O attack that carbon, because that carbon has a partial positive charge, breaking the pi bond with the oxygen. This then results in this structure. So, now we see the the positively charged oxygen over here, or getting deprotonated by that water, resulting in this structure here. And we see this oxygen form a pi bond with this carbon, breaking the pi bond between that carbon and the nitrogen, leading us to this structure with a negatively charged nitrogen. This nitrogen then is protonated by the H3O plus, leading to this group where the water in solution that's been deprotonated now is protonated again by this alcohol, resulting in this structure here where we see this oxygen form a pi bond with the carbon, breaking that carbon's single bond with the nitrogen, resulting in this structure with a negative charge on the nitrogen, which then takes a hydrogen from the H3O plus, resulting once again in our product for both of these reactions.